Hello, my name is Fernando Centurion, and today I want to talk about a really nice idea. What happens if we combine neural networks with Monte Carlo randomness to simulate fluids? Fluids are chaotic, they form vortices, rings, swirls. They're messy. But underneath all that mess, they're actually following a very precise set of rules known as the Navier-Stokes equations. So that's where we start. The Navier-Stokes equations are basically the rules of the universe for how fluids move. It looks like this, but let's break it down like a recipe. U is the velocity, it's how fast the fluid is moving. P is the pressure, that is the quantity that pushes fluids around. And G is any external force like gravity if they apply. And because we're talking about incompressible fluids like water or smoke in many cases, we add this quantity right here that simply means the fluid never gets squeezed or expanded. Basically, the whole game is track velocity and pressure over time while respecting this no compression rule. Let's examine the variables a little bit. Precisely, let's look at the velocity. We can see that it depends on space and time. So if we want to discretize it, we have to do it in both space and time. Surprisingly, simulating fluid over time is not as scary as it seems. A classic method splits the update into 3 bite-sized steps. The step 1 is advection. That we can interpret it as every piece of fluid moves along whatever direction it's currently going. We move to the step 2, pressure projection. This step enforces incompressibility. We compute pressure so the fluid doesn't inflate or deflate. And finally, we have the velocity correction. Basically, pressure fixes the velocity to make everything physically correct again. We can repeat these steps and we have a simulation. Now comes the big question. How do we store the velocity field? Traditionally, we use grids. That's what almost all solvers do. Imagine just dividing like the whole domain into tiny boxes and storing the velocity at each grid point. That works, but it's not perfect. It's hard to represent the fine details. It needs lots of memory. It's not smooth. It's tricky with complex shapes, and the interpolation is just unnatural. Basically, for example, if we have a point outside, that doesn't belong on the grid but is on the middle, like this red point right here, we have to apply some interpolation, which is basically approximate values, but we're losing very important information over there. So what if we don't use a grid at all? What if velocity is just a function that we can evaluate anywhere? That's where neural networks comes in. A neural network takes a point and returns a velocity. This is called an implicit neural spatial representation. And it's awesome because it's continuous, it works at any resolution, it's adaptive, and gradients basically comes for free because it uses auto-differentiation. Basically, in theory, neural networks should be perfect for fluids. But we have a problem. Neural networks really struggle with boundaries. Imagine you have a cylinder in the flow, as we can see here in this fluid representation, and the cylinder will be like this circle right here. You can imagine that you're looking at from the top or from the bottom. And the fluid should not penetrate the cylinder, of course. Previous neural networks enforce this by adding penalties in the loss function, but this only encourages network. It doesn't force it. So what happens? Basically, the pressure becomes inaccurate, velocity leaks into the object, and the simulation explodes. Vortex shading disappears, and the artifacts we can be present at the boundaries. For example, in this previous work using also the same approach, we can see that in the boundaries right here we have some artifacts, and of course it's like quite noisy, as we can see in all these surroundings. We can actually see this in older neural methods, and the flow around the obstacle is quickly becoming noisy. So we're going to use a really clever trick, that is the hard boundary trick. The authors of this paper fixed this with a very clever idea. That is, as we said, the cutoff function. We compute the distance from the point to the obstacle surface, and we set a distance epsilon, as we can see here. This blue line right here will be like the obstacle boundary, and we set this distance epsilon right here, as we can see by the pointed line right here. When the velocity vector is outside the distance epsilon, it remains unchanged, but when it is within this distance, it will become gradually to zero until it finally reaches the boundary, when it becomes exactly zero. To get this behavior, the paper uses those functions. Specifically, we are going to use the linear cutoff function because it's simple and it remains one outside the distance and linearly goes to zero between that distance epsilon. So finally, the velocity becomes this expression right here. This guarantees that the fluid sticks to the walls. There's no discontinuity introduced because we are just making it going to zero, not just exactly zero, just abruptly to zero. The neural network never cheats, and the boundary conditions are exact, not approximate. This one trick fixes half the issues that we used to have with the neural simulations. So let's take a look to the other half, the pressure projection. Neural networks had trouble approximating pressures, especially because pressure comes from a Poisson equation, which is a second order partial derivative PDE, which is very sensitive to errors. Here's where Monte Carlo methods comes to rescue. In this, instead of solving the Poisson equation with a grid, Walk-on stars uses random walkers to estimate the solution. Basically, we can explain the super high level idea, like start a random walker at any point, so after that we let it bounce around until it hits a boundary. We are going to use this method to leverage the mathematical probabilities to compute pressure. This method has some big advantages. For example, it works perfectly with complex shapes, naturally respects Newman boundary conditions, and produces pressure and exact gradients. No grid, no mesh, no Laplacian discretization, nothing. So at the end we get a neural network for velocity smooth, which is smooth and continuous, and the Monte Carlo for pressure, which is robust and it's boundary aware. The good part is that they complement each other perfectly. At the end, we get the final algorithm, which is quite simple but also very powerful. So at each time step, the neural network will compute the advected velocity. The second step will be like the Monte Carlo step will compute the pressure. And finally, the neural network again will compute the corrected velocity. with, of course, those hard boundaries that we talk about. We have also one more important detail we have to add. That is basically the neural network weights are resets every time step. This basically prevents the model from accumulating noise or getting stuck. Okay, we can take a look to the results. That is basically the fun part of it. Here we can visualize the von Karman vortex tree. That is basically a classical fluid experiment where we have a cylinder which is placed in a flow, and after a while the flow that we can see flowing here, it forms a pattern alternating vortices, which is called the vortex street. Previous neural networks failed to generate it. They became noisy almost immediately. But this method, it actually reproduces the vortex shading. There is still some noise, as we can see right here at this neighborhood, but the phenomenon is clearly there, and this is a huge achievement for a purely mesh-free method. A second experiment that we can replicate with this method is the smoke ring colliding experiment. As we can see at the left hand side, we have the real life experiment where basically we have two smoke puffs colliding and forming a ring, as we can see here, and our method captures, as we can see here, the torus shape, the outward expansion, and the rotational behavior. Some small scale vortices maybe are missing, but the overall structure is there. And finally, we have the fluid and obstacles. When fluid hits a sphere, as we can see here in the simulation, the flow obeys that boundary. There's no leakage, no artifacts near surfaces, and it's a very clean result. And this was a major weakness of previous neural solvers, which this method can solve it like cleverly. But of course, this method, it's not perfect. We still having some limitations. It's still being slower than the grid methods, unluckily. The Monte Carlo introduced variance, that is basically noise. Some symmetry breaking smoke. We can have it like in the smoke rising test, the symmetry breaking. Basically requires tuning, network size, and sampling. Not yet competitive with classical solvers in accuracy. But considering that it's a mesh-free method, the results are impressive. The authors just propose some future directions for this work. How to combine neural networks and Monte Carlo in a training framework. Can Monte Carlo noise be reduced for faster convergence? Can we reuse those neural network weights across the time steps safely? And more advanced architectures for learning physical fields. Can we actually achieve that? This is a very open problem actually. It has lots of exciting future work. So we can give like a quick summary. To summarize, we solve the Navier-Stokes equation by only splitting time into 3 steps. Velocity is represented as a neural network. The pressure is solved by the Monte Carlo method. The hard boundaries are enforced with cutoff functions, and this hybrid method produces credible vortex shading, smoke rings, and obstacle interaction. All of this is done without any grid or mesh. It's a beautiful combination of mathematical physics, probability, and modern neural net methods.